Well, this is work that I've been doing with Sibren. I don't know if he's online. In fact, Sibren is the main inspirator of this project. He was already starting to do that with some students, and I took over more or less during Corona time. So it's already going for a couple of years, slowing by slower. But I think we are now at a stage that we have some results that I want to share now. I'm trying to go to the next. There it goes. Oh, it goes not that fast. Yeah, it's about what? It's about the interaction in the Atlantic major overturning circulation and the NAO. Well, I don't think I have to explain this. What I want to mention that we are using in our analysis the rapid array data shown here in this plot. Of course, NAO is also something I don't have to explain in this audience. This is a picture from ERA5, and a positive NAO is when the pressure at the Iceland area is lower than normal. Okay, what we have been analyzing is 15 high-risk models, 100-year control simulations, 1950 conditions, and in addition to that, rapid ERA and ERA5 solely as well. And we are looking at the winter season, December, January. If necessary, we did some non-linear detrending, especially on the AMOC signal. The AMOC is defined here as a strength at 26 north in Sverdrup, and we are using different lags and always using 5-year running means. A negative lag is meant here, atmosphere is before the ocean, and positive lag, the atmosphere is lagging the ocean. Okay. The signal is going, oh wait, I think I have to do it with my mouse. Okay, sorry. When we computed a lag correlation analysis with the NAO, the mean sea level response signal, that's defined by those two boxes here. That's my definition of the NAO. With the AMOC, you get this picture where the lag is in years. So that is the atmosphere is before the ocean and positive, the atmosphere lagging the ocean, and you don't see any reasonable signal, at least only at lag null. There's a clear signal. I come to that later, but especially in positive lags, there is a lot of positive and negative correlation. So what we did is, and that was an idea by Sibren, I must say, all the good ideas are coming from Sibren. So he said, well, let's split into negative and positive NAO models. Negative models, that's our models that have positive lags of the atmosphere and negative NAO sign, and the other models then has a positive NAO sign. And below you see the different models, and there were two models we couldn't decide what to do with them, so they're outside this division. And we are also using rapid ERA, and that was motivated by an article by Smith. I think many of you have been co-authors, and the title is North Atlantic climate far more predictable than models imply. So instead of 100 years for a real reliable signal, maybe 20 years or 18 years now is sufficient, and we will see how that works out. So if you then make a model mean of those two groups, then, and I've plotted the model mean lags -3, lag 0, lag +5. You have the negative NAO models that shows at lag +5 definitely in positive NAO signal as we made by the selection, and at lag -3 positive NAO. The positive NAO models, they don't show a signal. They keep more or less weakly negative lag -3 and lag +5 as well. And if you could do the same for the rapid, then you see a similarity between the negative NAO models. All models show a strong signal at lag 0. And that might seem strange, but this was already noted by Polo et al., and I think that is well, more or less known, at least by part of the community, that at lag 0, the AMOC response is dominated by the Ekman transport. So that is not driven by buoyancy forcing, but by the wind forcing. And that I don't will speak anymore during the rest of my talk. But the signal that is only at lag 0 still is visible if you average over 5 years. So it's a signal at exactly at lag 0 due to the wind forcing, but if you average over 5 years, you still see it. Now, we had the idea that this difference between the negative and the positive models are due to the ocean-atmosphere interaction. And we did this to visualize that. We did a regression of the SST on the AMOC, and I'm now always focus on lag -3 and lag +5, where the signal are strongest. And they see at lag -3 for the negative models and a negative S signal in the subpolar gyre, and at lag +5 and also, but then also a signal in the subpolar gyre, but then positive. For the other models, the positive NAO models that don't show a really signal at lag +5, you don't see that in the SP subpolar gyre, but instead you see a signal in the Gulf Stream of similar, of a sign negative for lag -3 and positive for lag +5. And if you compare then that again with the rapid ERA signal, then it suggests that the negative NAO models are more similar to the rapid ERA 5 signal, with a negative value of the in the subpolar gyre for lag -3 and positive values for lag +5. Yes, that's for this slide. And then, of course, as we did, you can compute a lag correlation analysis of the SST averaged over this subpolar gyre box shown here. And then you see for the negative NAO models, as expected, a nice signal at lag +5. But for the positive models, you don't anything. And again, for the rapid ERA 5, we see something that's more or less similar for the negative NAO models. So that is again reassuring. The next question you want to answer, well, this SST plop in the subpolar gyre, is that forced by the atmosphere or forced by the ocean? Of course, we know that if we have an enhanced NAO, it will cool the ocean, and by the positive of a negative NAO, you would also expect a warming of the subpolar gyre. To figure that out, what we did was to do a regression not on SST, but also on the turbulent heat flux, and positive is here upward. So if you look at lag -3, you see a cold SST, and where there is the maximum, the upward heat flux is minimal compared with the area around. So this almost 0. So this cooling cannot be forced by the atmosphere, and then the other argument, then it should be the ocean. At lag +5, that's even more clear. You see at lag +5, that warm blob. The plots on the left-hand side have been shown before. You see the warming of the SPG at lag +5, but you see also a positive heat flux, so the atmosphere trying to cool that heat blob. So that is clearly forced by the ocean, and the atmosphere tries to cool it. If you do the same for the Gulf Stream, for the positive NAO models that don't have a signal in the subpolar gyre, but appear to show a signal in the Gulf Stream, and the mechanism appears the same, that the Gulf Stream signal by the positive NAO models is forced by the ocean, and we think by the AMOC, but at least by the ocean it is forced. If the SST and the turbulent heat flux have the same sign, then it is forced by the ocean. That's the easy way to remember the forcing by the ocean. If they have opposite sign, then it's forced by the atmosphere. Well, you can do this, of course, the same for the rapid ERA 5 data. And that's not completely convincing, but there is some indication that the SPG is indeed also forced by the ocean, because you see here the cold temperatures, but not that strong latent heat flux, suggesting that there is a component by the ocean. And here as well, by lag +5, you see a warm SST and not that strong turbulent heat flux trying to cool it, to warm it. So we think it's the ocean. Of course, rapid ERA 5 is only a limited period, but ERA 5 this has a long period. So it's tempting to look only at ERA 5, and we did that. And what you see here is I did it from here 1981 to 2023. Also again with 5-year randomness. I also did it for 1940 to 2003. The results are similar, but I used 81 because that's the area we trust ERA 5 mostly. Before that, I don't at least trust that very much. And then you see again what I did here is regress the SST over this average over this subpolar grid box, which is itself. So then of course you see that the maximum regression is within the grid box, and you see kind of a dipole. But you can then also regress the SST over the turbulent heat flux, and there you also see more clearly than only for rapid ERA 5 that over that area the turbulent heat flux is really much less than, for instance, in the Labrador Sea, whereas the signal is larger, suggesting that a large part of that SST is indeed, or significant part of that is forced by the ocean. And we can also do, and the same applies for the Gulf Stream, the Gulf Stream signal seen here, and that's also forced by the ocean. Well, that is probably not as surprising. And of course, you can then also make a regression, not with a lag, but at the same time, because the atmosphere always responds directly to any forcing, at least within a season. And then you can do a regression of the SST of the subpolar grid box on the mean sea level pressure, and then we see again a nice negative NAO in agreement with the models. Then, of course, if we think that this all makes sense, you can ask the question, how is the atmosphere forced by the lagged SST response? Well, this is, to my opinion, related to forcing of the storm tracks. In the winter, everything is dominated what the storm tracks do, and then the NAO is just a response of stronger or less strong storm tracks. Until now, we have been only looking at the SSTs, but if you want to understand how the atmosphere is forced, you have to go a bit upward in the atmosphere to the 850 hectopascal level, day 850. And then you see that for the negative models, there is, you see here the warming of the subpolar gyre warming, so that is also visible upwards in the air, and that is in agreement that the ocean is forcing it, and then this signal is transferred upper in the atmosphere, and you see also the signal of the colder Gulf Stream. And then this induces a reduction of the meridional temperature gradient. So it is in climatological, it's here cold, it's here warm, and then you have baroclinic instability. And if you have here warming and then cooling, you reverse or decrease this meridional temperature gradient. This is also seen in the rapid ERA5 results, and not seen in the positive models. That is in agreement with what we think. And you see it also for the ERA5, 1981, 2003. Then you see also this reduction in the temperature gradient. So based on that, the idea is that for negative NAO models and rapid ERA5, a reduced meridional 850 temperature gradient will induce reduced baroclinic instability, weakened storm tracks, and finally a negative NAO response. So I think this is not new. I think that is discussed in many papers how the atmosphere forces the NAO. Then I come to, maybe for EERIE, the most interesting part, the AMOC forcing and the evolution of SSTs. If you now regressed the AMOC at lag -3 for the positive and the negative NAO models, you see a strong difference in the deep water formation. What I plotted here is the mixed layer depth for people downloading data. It's emblotted, and you see quite a difference. The negative NAO models really show significant deep water formation around the Jin Sea. And here, and also in the more in the Labrador Sea than in the Jin Sea, whereas the positive NAO models that we don't like so much, you don't see that much deep water formation. A big problem, well, I don't know if it's a problem, but there's an issue, that the negative NAO models have a much larger bias with respect to the observation. Thurman has recently written a paper about that. He said, well, this, especially the high resolution models, show an overestimation of the mixed layer depth. I have no answer to this issue. I don't think, I have been looking at the turbulent heat flux. You don't see that much, and I don't know if a bias also implies a bias in the response to the AMOC. Maybe it's a climatological bias and that the response is still working okay. It's something that I have to work out. But yeah, this is at least an issue, I would say, that we have to investigate further. And then how is the SSTs are? What kind of evolution do we have? First the nice models, then you see this cold blob, and at lag -3, and then at lag 0, it's progressing the warm area. You see developing this here warm blob, and at lag +3, there is already this warm blob is there, and at lag +5 even more. Whereas for the positive NAO models, we don't see this progression into the subpolar gyre of the subtropical SSTs. And if you then again compare this with rapid ERA 5, you do see, and here goes quick, a progression of the warm subtropical waters into the subpolar gyre, supporting this idea. Then comes the question, what is determines the difference between the negative and the positive NAO models? There's two things that we have been looked into. That is the bias, and of course, because we are analyzing high-res map data, resolution, of course, comes around the corner. So we have been looking through that. What became clear to us is that there is quite a difference in bias between the negative NAO models and the positive NAO models. So that is, and the positive NAO models has a clear, much larger bias than the negative NAO models, especially in this area. The importance of this area has also been discussed by the response by Panos. I think Malcolm and me were co-author of that, so that has also an impact on the response, but apparently also for how the AMOC response is responding. This thus is even amplified response by the 2-meter temperatures, and that is due to the sea ice response, because if you have colder temperatures and a bias, you get more sea ice, and that really gives a strong feedback over cold temperatures. So this is, I've been sorting that out in detail, but if you look at individual models, if they're really cold, they have an enormous amount of sea ice bias, and the 2-meter temperatures become even more colder, even stronger bias. Well, then that's the idea of, well, is there a relation then between this SPG bias and the NAO response? And I made this scatter plot. It's not perfect, but at least it suggests that the bias is indeed responsible for the NAO response. And the yellow dots are maybe the good models, the negative NAO models, and the blue are the other models. I've combined the positive plus the two models that didn't have a clear signal altogether. And you see, well, more or less a linear response, although it's not perfect. And there are two outliers. I will come to that they are a bit funny, and that make clear that bias is not everything what counts. And I come to that. But the bias, that is also not a new idea. Very recently, there was a paper by Kim et al. And he discussed the authors of that paper discussed the effect of the bias for the forcing of the AMOC. And well, that is an agreement what we find. We did find, and then we saw the paper. They said, okay, we are not that stupid. And its argument is that if there is a strong bias, you have a much stronger stratification, and you didn't get that good deep mixing. So this is an agreement, what we said, and Kim analyzed, I think, a whole bunch of CMIP6 models, if I remember well. Apart from the argument by Kim et al., I think there's also another argument. That's more or less an atmospheric argument, and I am from a background of atmosphere, so that's always what I'm looking at. Is that you have this cold high, warm low mechanism. If you look at Z500, you do see did the negative NAO models have a stronger signal than the positive? But if you do then the same by the mean sea level response, the negative NAO models, they have still the signal, but the positive NAO models is completely disappeared. And my hypothesis is it because of the cold temperatures, especially when you have this sea ice response, you get very cold response, and you get this cold high, warm low response by the atmosphere, due to the surface boundary conditions. So that is an additional mechanism why, if you have a bias, the atmosphere is less able to force the AMOC. I haven't quantified this, but these are what I think the two mechanisms, the one by Kim and the other one, this cold high, warm low mechanism. So, but then what is the impact of the resolution? A PhD student passed during high-risk MIP, Remco Klaver, has analyzed the atmosphere models in terms of their effective resolution based on the energy spectrum of those models. So you have the nominal resolution, but probably a better metric for analyzing the real resolutions is look how much the real spectrum is distorted due to the resolution. And he wrote a nice paper about it. And based on that, you can group the models in 4 groups. High ocean and low ocean, of course, 1 degree and a quarter degree for the high-risk MIP models, and the high ocean are then also divided in 2 groups: very high resolution and high resolution, and low resolution and very low resolution for the ocean. And the funny result is that the very high risk models all belong to the negative NAO response. And then you have in between, they don't positive, they don't give a good signal. And you have a group with very low resolution. They do it also quite well. And it is quite puzzling. My hypothesis is that these very low resolution models are well tuned. So for high resolution models, I can remember when I was a high-res MIP, there was hardly any time to tune it. You had to build the model, struggle a lot with everything, and then give it a go. Especially with ETH, we had big problems in tuning. The deep water convection was, we didn't have any AMOC in the beginning. Everybody was panicking, but in the end we do. So it was really a nightmare. But for the low resolution models, you can tune endlessly and get nice behavior. I don't know if that is the cause, but that's my hypothesis. And these were also those, I encircled these 2 models that were the outliers for the bias, because you see that they have quite a strong bias here, -3.3 and -2.7 for the CNM LR. So they are outliers, but still they have a good negative NAO. So our hypothesis is that it's all due to the ability to be able to generate deep water formation. And I didn't know that Malcolm was the moderator, but I put here all the Hutchin models, and it's nice is because that gives 4 models that are basically the same with different resolutions. So it gives a nice agreement, nice comparison of the models. And you see that the H8, this the 10th of 12th of a degree and 25 kilometers horizontal resolution, gives a very nice deep water formation response at lag -3 when the AMOC is forced. HM goes a bit less, MM is not doing that well, but then LL is doing it nicely again. And CNM is also a model that belongs to the positive NAO models, but has also some deep water formation here, but that compensated by the deep water formation, the negative value over here, but that is associated with strong sea ice formation. So when you get sea ice during the during the positive NAO, then you get a reduction in the NAO. And ECUs, this is a model that's not doing given a response of a negative NAO at lag +5, and that is also not giving a good deep water formation. Based on that, how many minutes? I think I'm nice in time. We made this kind of scheme, what we think how the NAO and the AMOC are interacting. So you start with a positive NAO, and that's cooling the Nordic seas, gives an increase of deep water formation and an increase of AMOC. And that only works good if you don't have no or a weak cold bias. Doesn't work well if there's a strong bias. Then this interaction is weak, indicated by these arrows that are a bit wiggling and the dark color. And then the increase of the AMOC is not enough to have really go a substantial more forward attraction of the subtopical SSTs, the more SPG, weakening of barrier clinical instability, and finally a negative NAO. And this whole process takes about 8 years. And of course, I spoke about here cold bias, but I discussed it as associated with resolution, and there is also the impact of what you can do by tuning. But this is, from those three, I think the bias is the most relevant one, we need to minimize that to really trust our models. If this is true, this mechanism, then you should expect a really nice relationship between the deep water formation at lag -3 and the NAO response at lag +5. And then you see this very nice response. So it's really crucial what is your deep water formation at lag -3 in order to have this response at lag +5. And there is this outlier here. This plot I made last week. One was with my family in law in Brazil. This plot I made the average over the laboratory and the GNC, and I have to split that to see the maximum of those two, and to choose which region is most important for every model to do that. And I think then the plot will become even better, and at least this CNM LR model will switch somewhere to this area. But at least even under this not that sophisticated way, you see a very nice linear relationship between the deep water formation at lag -3 and the NAO response at lag +5. Okay, I'm almost done. This is something funny, and that was a question that Cyril asked me. He said, well, Rein, the whole discussion, I started with a positive NAO going to a negative NAO, but in terms of relationship, it should be completely linear, and you should be able to change the sign. However, if you do this, and I split the data in the values when the AMOC was negative and when the AMOC was positive, and you see completely different behavior. So for positive AMOC, then you see a really nice response. That is for all AMOC values. And here for the positive, then you see even stronger. But for the negative AMOC, you don't see any signal. We have a hypothesis, but we haven't investigated yet. The similarity with El Nino comes to my mind now. Because also for El Nino, you can, in linear model, it goes exactly up and down, but we know from experience, from observation and better understanding, that El Nino is not completely symmetric. We have much larger El Ninos than La Ninas, and you need that there is sufficient heat in the warm pool, in subsurface warmth, and then you need them westerly windbirds to get everything going on. I have not completely figured that out. But my hypothesis that something might also be true for the NAO AMOC interaction, that if the AMOC is in a good phase, and then you need not on westerly windbirds, but due to natural variability, some strong NAO forcing, and then the AMOC responds in a nice way, and you get a response 8 years later. So that would then be the time scale, and it would be not really an oscillation, as we don't also have for the ENSO. You see kind of dominant time scale, but no one sees ENSO as a nicely oscillating thing. It's a burst popping up now and then, and I think this, to me, this would be a very useful way for further investigating the NAO AMOC interactions. What is preconditioning by the AMOC, and then the atmosphere being able to give it a nice kick. Okay, 41. I think I'm nicely within time. Before some discussion, people has to go to to drink some water, to the toilet. So the different behavior of Primavera models with respect to the AMOC interaction, and the SST bias appears to be the main cause for the different behavior. Resolution is important to reduce the bias, but as I see from the models, tuning can compensate errors, and I think tuning is important. I'm now employee of BSc and ETH, and I think the fact that ETH is not doing that well in high-risk map, it doesn't mean that this is a pertinent problem for ETH. I think really looking into how it's tuned and how it's doing. And I think the main issue is really to look how the deep water formation is doing, because as I understand, that is really crucial for the AMOC NAO interaction. And also I think that rapid ERA5 is supporting our results. That is really, and that's open for discussion. We can discuss a lot of things, but I think it's crucial to reduce the SST bias in the SPG and the CIS bias and the tendency. And maybe, I know this is a kind of crossing in a church, but maybe can be used for decadal predictions, flux correction, because for climate change you don't want to use that, but maybe for improving the skill, this might be an idea. But that's something we can discuss. Now, this is, I think, is demanding. If otherwise the EU gets mad. So this is the funding slide, and this is the end.
Awesome, thank you very much. That was great. Very, very interesting. Yeah, lots of things to think about there. Yeah, great. People have questions, please.
Shall I stop sharing?
Maybe
not.
Keep sharing for a minute, and in case you need to refer back. people put their hands up, although because I'm on the browser, I'm not entirely convinced I get to see hands. So if I don't call you, just shout if you have a question. So does anyone have a question?
I'll go to the discussions, conclusions, discussion.
I had a kind of initial question, and not being an NAO expert, I'm not sure if it makes sense. Could you assess the NAO variability in the models, and is it obvious compared to doing the positive negative? Is it obvious to note which models didn't have such good NAO variability, or is it too short, or is that not well defined enough?
Yeah, we have been thinking by that also on the AMOC. So we have, I don't know if I did it for the NAO, but I did it for the AMOC. But I was expecting to see quite some difference in AMOC variability between those two types of models, but I couldn't find. There is some difference in the autocorrelation. I don't have the plot. You see that the autocorrelation of the say the good models, so let's call them for the moment to make it. Otherwise, I'm always mixing up positive and negative. But let's call them the good models. They have their autocorrelation time scale is long. So they keep their sign.
Okay, right.
I haven't done that for the NAO, but I think it's a good question to see if the NAO behavior is different in those models. 5 years.
Okay. Michael has a question here.
Hi, Ryan. That was really interesting. I have quite a few questions actually, but that provoked a lot of thoughts. One question is, you were comparing the model over the historical period with the ERA 5 and rapid data, especially in the observations. Have you thought about how you might be able to separate out the influence of aerosol or other external drivers? Because both the AMOC and NAO changes there could be due to a common background driver. It's not, I think it's a bit more difficult in the observation to really pick out the AMOC NAO links, especially with changing aerosols and so on in those periods.
I know. I've thought about, and I know the issue. Of course, there's literature on that the AMV is forced, I think, by Boots and this kind of papers. No, it's a good question, and it's I don't know. You would like to eliminate from the data the radiation forcing to eliminate that from the simulation. To me, it's a good question to think about it, but I don't have a clear answer. No.
Okay, thank you. Yeah, I think in the models there are there aerosols in the high risk models?
Yeah, but I think. Sorry, go on, Rein. Yeah.
No, go on. You're more the aerosol expert.
No, well, so I was just going to say that I think Rein was looking at the control 1950, so they're constant.
Yeah.
Okay.
So and because they're high risk models, they use this. They're not evolving predictive aerosols. It's kind of a climatology. So and all the models more or less have that same climatology. So in principle, the models are not year to year being forced by aerosols in different ways. Yeah. So please, if anyone else has a question, kind of shout, because I don't see any hands. But then my browser doesn't Michael has more, so shout out first
Yeah.
to get in front of the queue before Michael's next one. No? Okay, Michael, go on.
Okay, I'll ask mine now. So, how important do you think the AMOC forcing is for the total NAO variability? Have you looked at perhaps how much does the AMOC force NAO explain compared to the total NAO variability? So it's kind of similar to Malcolm's question, I guess, but how much of that does it explain?
I can give an answer, but to be honest, I need to. It's a very good question, I think, and maybe there is a way to figure that out and to do some analysis to figure that out. Which at least within the models, for the reality, it's probably hard to do. But I guess we do have. We don't have high-risk map simulation with some concept. We only have. At least you want to. Well, I can compare the models that don't have a really response to the models that do have a good response. That's probably the first way to analyze it. That gives then probably within this setting some idea how important it is for the total variability.
Yeah. Okay.
That at least, but it's a good point. That's something comes on my to-do list. It is also would be also very nice because my idea is that there's this thing that's going around and also about the signal to noise ratio. I have the feeling that part of the problem is that, as I see it, that you together with all the models that have maybe a reasonable NAO response and models that doesn't have any NAO response, you get a really much smaller signal. But I don't think it explains everything. I don't know. But this your question would then give at least maybe some hint how important the forcing is by the model, and maybe that is still too small compared with real atmosphere.
Yeah.
Because it suggests what I've seen so far is that the models suggest a signal, but that it's not as large. That the atmosphere does.
Yeah. Yeah, and I guess some of that is tied in potentially to the bias, right? Because I know the seasonal monthly to decadal group here went to a quarter-degree ocean, partly because of the reduction in the cold bias, which also influences the zonal wind bias and gave them much better predictability. And then, as you said, Panos's paper kind of suggesting some of those links as well. So I think there's lots of interesting links between those different things, like what you talked about as well. That there's hints of various of those things interacting in that, and that maybe a signal to noise is also then part of a combination of those various things, plus maybe some other things that we don't quite know yet.
Yeah, but I don't know if Nico is part of the audience. That I will share this plot. Here, this plot What I want to do is to put ERA 5 here in. If we have, I need observations of, or at least estimates of the mixed layer depth in those regions. The NAO we know quite well, and we have rapid air. We have the AMOC of the rapid period, and see where then say that dot that might represent observation, where that would be. That might also give an indication in how the atmosphere is comparing with the models. At least a first guess of that.
Yes, that would be very interesting. Yeah. Yeah. Great. Anyone else?
I had a comment and a question. Okay, so here for the mixed layer depth, maybe you can use the outputs from ORAS 5, which should be quite compatible with ERA 5, I would guess.
ORA 5, yeah. And
I know they have issues, but it's a bit further south. They have some non-stationarity bias there. But I think in the Labrador Sea, you should have reasonable estimates of the mixed layer depth.
And that's available on monthly mean basis?
I think so, yes.
Okay.
And then my question, it's a bit technical regarding the analysis. I remember having done similar plots in the past, doing some correlations between the NAO and the AMOC. And there was something tricky about that because you have one signal that is common, but it is not necessarily implying that one is the NAO is forcing the AMOC, and it's the Ekman transport. So especially in the case that you're showing here, that you have the water formation lagging by 3 years the AMOC. What happens usually, let's say the thermohaline driven response of the AMOC is forced by changes in the water formation, and they're usually leading by 3, 4, 5 years. But then you have an in-phase relationship that is the Ekman transport. So instantaneously with the NAO, you always have some correlation because the Ekman transport happens at the same time. No? But it's not the kind of signal that you want to see when you're looking at the AMOC. Did you address that in any way?
No, we didn't address that. I have been thinking about that.
So what I had done in the past was to remove the Ekman transport and then to check the remaining signal. No?
Oh, the Ekman transport in the AMOC, you mean?
In the AMOC, yes.
Yeah. That's something I know that Rapid has this. You have the total AMOC and you have the Ekman driven signal. I think in the models probably you can do the same as well.
Because also Ekman is opposite sign in the tropics and the subpolar latitudes. So it was usually confounding things when you were looking at propagation of signals of the AMOC from the high latitudes to the low latitudes, because you were finding very strange behavior and like the AMOC would be leading the NAO, but in a way that you wouldn't expect. And at the time we were doing it that way. I can check and we can discuss it, what it did in case it can be useful for the analysis.
Yeah, it's a good point. What I've seen is the AMOC response is really strong well, it's dominant at lag 0.
Mhm.
And then, but I agree, it's interfering with the buoyancy response. But at this moment, I don't have a clear idea how strong it is. But that's a good point to figure out.
That was it.
Yeah.
Thank you.
Great. Thank you very much. Just to make sure.
Can I have
that
a short interruption, Malcolm?
Very short, because I.
Yes, no, just about the Eggman. So you should not forget. So if we do not any filtering, then the Eggman is completely dominant. But all we show is our results with a 5-year running mean, which I would guess would kill most of the wind-driven variability in Eggman. But apart from that, I think Pablo's point is good, and we will look into it. But yeah, it's a 5-year running mean that should be realized.
That should minimize the problem for sure. I don't remember to extent that was solving it completely, but that should for sure minimize it. Yeah.
Great. Well, yeah. So I'm going to wrap it up before the hour. So thank you again, Rein. That's been really interesting and generated lots of discussion and interesting questions. So I really appreciate you coming along. And thank you everyone for coming.